I am Burcu Savaşkan from Karadeniz Technical University in Trabzon, Turkey. And I have been working processing of bulk superconductors and magnetic characterization, especially magnetic levitation force. Today my presentation is magnetic levitation force of bulk MgB2 for different permanent magnetic guideway. Since the discovery of superconductivity in MgB2 materials at 39 Kelvin, enormous efforts have been made of processing, characterizations, and applications. And its superconducting transition temperature is lower than the other high TC. But it allows its BCS features allows a large coherence length and a high critical current density. I try to gather the other advantages of this material, so I called why is MgB2 is so special. As known, magnesium is type of common metal, so we suggest low material cost and short processing time and relative easy of fabrication. Today, in bulk MgB2 can be prepared by spark plasma sintering in less than 2 hours. And its BCS features, MgB2 coherence length is quite high compared to other high temperature superconductors, and maybe the most important feature is the lightweight, because due to lower density and lower anisotropy and high JC. In bulk MgB2, the grain boundaries don't form a strong barrier to current flow, and the ability of the grain boundaries support the supercurrents and don't show any weak link behavior like in cuprates. And higher mechanical strength, the ceramic nature of rare earth barium cuprates arise or cause brittleness and low mechanical strength, but maybe counterpart MgB2 presents maybe it's easy fabrication, large dimension of different types of bulk superconductors like these images, and it can work, MgB2 can work liquid neon and liquid hydrogen, and it is rare earth free material. All these features makes it an exciting candidate for industrial applications, and maybe problems arise. Its porous character because of percolative currents in polycrystalline bulk samples. And nowadays, the bulk superconducting applications may be two main categories. Firstly, trapped field magnets, and secondly, magnetic levitation devices. And it is quite obvious high dimensions and different shapes of materials are more and more desirable. And a bulk superconductor magnesite and applied field below its TC, it can affect this strong diamagnet, and concentric supercurrents induced within the bulk sample during the process, during magnetization process. And when the external field is reduced to zero, the supercurrents persist, and the resulting magnetic field, called as trapped magnetic field, its magnitude is much greatly using iron-based conventional permanent magnets. So I want to gather the trapped field records for bulk MgB2, and while rare earth barium cuprates can have high JC and so high trapped field values, such as today one rare earth barium cuprates record is 17.6 Tesla at 20 Kelvin in gadolinium barium cuprates, but it is difficult to shape high and large and high quality single grain samples over 60 millimeter in diameter. But other counterpart MgB2 is a homogeneous GC distribution within the sample, so cause the homogeneous trapped field distribution within the sample. It is clearly contrasts with the other cuprates or cuprate material, and this table shows or indicates records for bulk MgB2, and it is clearly seen a target trapped field value is 3 Tesla at maybe 20 Kelvin, and appears like modest value compared to cuprates. But today, only one bulk MgB2 magnet record is 5.4 Tesla at 12 Kelvin in 20 millimeter in diameter. And so we consider maybe bulk MgB2 magnets are similar melt-textured YBCO bulks. And bulk superconductors can act effectively strong diamagnet, and the ability of levitation is greatly enhanced by flux spinning centers. And a permanent magnet can stably levitate above a bulk superconductor. And the powerful demonstration is levitation of bulk superconductor, levitation large masses like a sumo wrestler in Japan, around 200 kilograms. And today, this introduction between a permanent magnet and superconductors over maybe 1,000 kilograms have been levitated. And magnetically levitated transportation systems, maglev, have vehicles to move with minimal friction and maybe too much speed and diamagnetics magnets are above the permanent magnetic guideways placed, and a prototype vehicles with seats for 2 people have been made in Germany, and this project name is Supratrans. Is an innovative transportation systems based on magnetic levitation force. And today a lot of numbers of groups working on superconducting levitation force, generally used rare earth barium cuprates as a superconducting material. Maybe while MgB2 bulks enters more and more application, but to date it has any considered maybe for maglev trains. And in this slide, I want to give some instance our research group activity in this field. And firstly, we investigated the effects of malic acid addition on magnetic levitation force of bulk MgB2, and we used two reaction in situ solid method, and we observed reasonable addition has a positive effect on magnetic levitation. And the other study, we investigated the size effect on magnetic levitation force, and we observed the magnetic levitation strongly depend on diameters, bulk and permanent magnets. And also we investigated the surface laser treatment on levitation force properties of regional silver addition to titanium doped MgB2, and we determined 2 times after laser treatment magnetic levitation force values enhanced 2 times. And in the present study, as you know, that there are a lot of several factors have significant effects on levitation force properties, such as reticle current density, the fluxability of superconductor, and size superconductor and permanent magnet, maybe shape, and there are relative configuration and measurement types, cooling types, maybe cooling regime, etc. And in this present study, we investigated magnetic levitation bulk MgB2 with different arrangement permanent magnetic guideway, and general in two different types arrangements are used. Firstly, conventional PMG and Halbach PMG. In conventional type, there are 2 permanent magnets in opposite magnetic direction, and iron or steel between them to concentrate magnetic flux distribution. And Halbach time, permanent magnets are used instead of iron or steel to concentrate magnetic flux distribution. And we focused on, in the study, maybe comparison of 2 types of PMG arrangements. And all measurements were taken. All measurements were taken. These systems in our university by designed Professor Öztürk, and he is both our research group. And before the measurement, experimental measurement, firstly we were simulated magnetic flux distribution within the sample because we want to see the effects on magnetic flux distribution on magnetic levitation force, and it is clearly seen in Halbach distribution, BZ and BX bigger value than maybe conventional, and this figure shows the vertical levitation force versus vertical displacement, and maximum levitation force value depend on or maximum value for PMG Halbach compared to conventional, and this in zero field regime and tubing heights we choose 60 millimeter, and it is due to magnetic flux distribution, because in this type, Halbach type, the bigger Bx and Bz value. And the other figures show the vertical levitation force versus vertical distance, different pulling heights. In a zero field cooled regime at measurement temperature is 33 Kelvin, and clearly seen when the cooling heights increase from 10 millimeter to 77 millimeter, and the repulsive force, positive value, increased, but the other part, cooling heights increased, but attractive force, negative part, is lower than compared to other, because this cooling heights, the screening, maybe screening current increased, but low trapped field. And summary, the maximum value of levitation force increases while cooling height increases for all PMG arrangement. The maximum levitation force decreases with decrease of field cooling height due to more trapped flux during magnetization process at lower cooling heights, and the levitation probability and stability of bulk MgV2 are closely dependent on this trapped flux. So more flux in lower cooling heights can bring a reduced levitation and a bigger guidance or better stability. It is very important as magnetic levitation force. Thank you.
Thank you very much for the nice talk.